Alkenes are unsaturated hydrocarbons consisting of a sigma bond and a pi bond. The typical reactions of alkenes involve the breaking of the weak pi bond to form two sigma bonds. Such reactions are called addition reactions. These addition reactions are usually electrophilic in nature, as the pi electrons of carbon-carbon double bond are available to any species seeking electrons. Let us study the following reactions in alkenes. Addition of dihydrogen, addition of halogens, addition of halogen acid, addition of sulfuric acid, addition of water, oxidation, ozonolysis, polymerization. Let's start with addition of dihydrogen to alkene. Alkenes react with dihydrogen in the presence of catalysts like finely divided nickel, palladium, or platinum to form alkanes. Such addition reactions are always cis addition reactions. For example, ethene in the presence of finely divided nickel, palladium, or platinum yields ethane. Similarly, propene yields propane. Now let's look at the addition of halogen to an alkene. Alkenes react with halogens such as chlorine and bromine to form vicinal dihaloalkanes. However, they don't react with iodine under normal conditions. For the reactions with chlorine and bromine, the alkenes and the halogens are mixed together in an inert solvent like carbon tetrachloride. Ethene reacts with bromine to give 1,2-dibromoethane. This reaction proceeds via the formation of an intermediate called cyclic bromonium ion. During the addition reaction between ethene and bromine, the reddish-brown color of bromine gets decolorized due to the formation of dibromoethane. Hence, this reaction is used as a test for unsaturation. Let us now look at the addition of halogen acid. Alkenes react with halogen acids to form haloalkanes. In the reaction with alkenes, hydrogen iodide is more reactive than hydrogen bromide, which is more reactive than hydrogen chloride. In the case of symmetrical alkenes, only one product is formed. For example, ethene on reaction with hydrogen bromide gives bromoethane, or 2-butene with hydrogen bromide gives 2-bromobutane. However, in the case of unsymmetrical alkene, two products are formed. For example, propene reacts with hydrogen bromide to form 2-bromopropane and 1-bromopropane. Of these, 2-bromopropane is a major product. This is in accordance with Markovnikov's rule, which states that during the addition of an unsymmetrical reagent to an unsymmetrical alkene, the negative part of the addendum is added to that unsaturated carbon which possesses lesser number of hydrogen atoms. In the reaction between propene and hydrogen bromide provides the electrophile H+ that attacks the carbon-carbon double bond, leading to the formation of primary and secondary carbocations. The secondary carbocation, being more stable, is formed readily. This secondary carbocation is attacked by the bromide ion to form 2-bromopropane. Hence, 2-bromopropane is a major product. However, the addition of hydrogen bromide to unsymmetrical alkenes like propene in the presence of peroxide is on the contrary to Markovnikov's rule and is known as anti-Markovnikov's addition or peroxide effect or Kharash effect, as it was first observed by M.S. Kharash and F.R. Mayo in 1933 at the University of Chicago. The peroxide effect takes place via the free radical mechanism. In this reaction, initially benzoyl peroxide undergoes homolysis to form benzene free radical. This attacks hydrogen bromide and results in the generation of a bromine free radical. This bromine free radical further propagates the reaction by attacking the double bond in propene. Hence, propene undergoes homolytic cleavage to produce less stable primary and non-stable secondary free radicals as shown here. The secondary free radical attacks hydrogen bromide to form bromopropane, and the primary free radical attacks hydrogen bromide to form 2-bromopropane. Thus, 2-bromopropane is formed as the major product. Now let us move to the addition reactions of alkene with sulfuric acid and water respectively. Alkenes react with cold concentrated sulfuric acid in accordance with Markovnikov's rule to form alkyl hydrogen sulfates. For example, ethene and propene react with cold concentrated sulfuric acid and form ethyl hydrogen sulfate and propyl hydrogen sulfate respectively. Alkenes react with water in accordance with Markovnikov's rule. In the presence of concentrated acids like sulfuric acid, a water molecule adds to an alkene molecule across the double bond to form alcohol. For example, 2-methylpropene reacts with water in presence of concentrated sulfuric acid to form 2-methylpropan-2-ol. Let us now look at the oxidation reactions of alkenes. Alkenes, on reacting with cold dilute aqueous solution of potassium permanganate, which is also called Bayer's reagent, produce vicinal glycols, that is, 1,2-diols. For example, ethene, on reaction with Bayer's reagent, forms ethane 1,2-diol or ethylene glycol. As the purple color of potassium permanganate decolorizes with the formation of glycol, this reaction is used as a test for unsaturation. Depending on the nature of alkene and experimental conditions, alkenes react with oxidizing agents such as acidic potassium permanganate or acidic potassium dichromate to form ketones or acids. For example, 2-methylpropene, on reacting with acidic potassium permanganate, gives propan-2,1 or acetone. On the other hand, but-2-ene, on reacting with acidic potassium permanganate, gives ethanoic acid. Let us now look at the addition of ozone to an alkene, which is also called ozonolysis. Alkenes react with ozone to form ozonides, which, on further hydrolysis, in the presence of zinc, form either aldehydes or ketones or both. For example, in this reaction, the ozone molecule is added across the double bond in ethene to give ethene ozonide. This, on hydrolysis, forms formaldehyde or methanol. The oxidation of alkenes by ozone to form ozonides, followed by its decomposition with water, is termed as ozonolysis. This reaction is useful in locating the position of the double bond in an unsaturated molecule. Let us look at another example of ozonolysis reaction of propene. Here, first propene and ozone react to form propene ozonide. The propene ozonide, on further hydrolysis in the presence of zinc, undergoes cleavage to form ethanol and methanol. The products formed helps us to determine the position of the double bond in propene as shown here. Let us move on to the last reaction, that is polymerization. Alkenes undergo addition polymerization reaction when heated under pressure in the presence of suitable catalysts. In this, a large number of molecules of the same species join together to form a giant molecule called a polymer. The simple compound which forms the polymers are called monomers. For example, ethene, when heated to 1000 degrees Celsius under 1000 atmospheric pressure, undergoes polymerization to form polythene.